In the previous lecture, you learnt about how time dependent charge densities and charge currents lead to potentials and fields that are calculated using retarded time. In this lecture, I solve 2 or 3 problems that tell you exactly how these calculations are performed. This lecture is on some problems on retarded potentials and fields calculations. Problem number 1, I am taking from Griffiths and extending it. So, this problem says that an infinite straight wire carries the current I t equals 0 for t less than equal to 0, and it is I 0 for t greater than 0. Griffiths calculates the retarded potential and then calculates the fields from this. I am changing this problem slightly and say that find the resulting electric and magnetic fields using direct formulas, and which I call Jeffimenko's expressions for these. Then of course, once I solve it, you can check it against the solution obtained by Griffiths. Solution. The way direct formulas work is that E at r at time t is given as minus mu 0 over 4 pi integration of d j at r prime t prime over dt prime, and this is calculated at retarded time times 1 over r minus r prime dv prime, that is one term, plus 1 over 4 pi epsilon 0 integration of rho r t prime gradient of with respect to prime variable. This is again calculated at retarded time divided by r minus r prime dv prime. So, there are 2 terms in this, and in our given problem j is not equal to 0, but rho is equal to 0. So, the second term will not contribute. So, this term will not contribute. We need to calculate only the first term. So, let us do that. What you are given is a straight wire along the z axis. Since I need the current density, I am going to write the current density J R t as 0 for t less than equal to 0, and it is equal to I naught delta x delta y in the z direction for t greater than 0. So, the way the current looks, if I were to plot it with respect to time, is that this is my t axis, this is j axis. It is 0 up to time t equals 0, and then at t equals 0 it becomes a step function. So, j is like a step function, it turns on at t equals 0. Therefore, dj dt RT is going to be equal to a delta function at t. Now, remember, when this is done in calculation of the electric field, this is all at retarded time. So, this t will be equal to retarded time, and that means t equals retarded equals t minus r prime over c. That is point number 1. Point number 2 is that because of the symmetry, when this current is going this way, E is going to depend only on the perpendicular distance from the wire. I am using cylindrical coordinates. And it is going to be cylindrically symmetric. What that means is there is no dependence on phi. So, my E field is a function of S and T, and as you can see from the direction of J, it is going to be in the Z direction, but we will calculate that. So, what I am after is the integral E S T is equal to integral minus mu naught over 4 pi j at r prime t prime, where t prime is the retarded time, divided by r minus r prime dv prime. Let us now put in things. Oh, this is d by dt prime. Let us now put in things that we have already displayed and do the calculation. So, I have E S t equals minus mu naught over 4 pi integral d by dt prime of j, which is I naught delta x prime delta y prime delta of t prime. Since I am already writing the derivative, so I am going to remove this part now, divided by modulus r, which again I am going to remove and say this is only s vector, and the contribution is going to come from only z part. So, z prime z d z prime d x prime d y prime, and this is calculated. Let me write it explicitly at t prime equals t minus modulus s minus z prime z over c, and therefore, this whole thing is minus mu naught over 4 pi, and I was missing the direction here, which I should write it as z. Z I naught comes out, delta x prime delta y prime get integrated over dx prime and dy prime. So, they go out of the integral, and I have only the dz prime integral over delta, which is going to be t minus the distance is now going to be square root of s square plus z prime square over c divided by square root of s square plus z prime square. That is my answer, and we already know that this is true for t minus square root of s square plus z prime square over c greater than 0, and it is equal to 0 for t minus s square plus z prime square over c less than equal to 0. That will set my limit on z prime integral. Just to recap what we have done, so that you do not get lost, we have a wire in which we switch on a current I 0 at t equals 0. So that the current is 0 up to time t equal to 0, and then picks up a value at t greater than 0. So, obviously, all the fields are 0 before that, and then as soon as you give this spike, if I were to plot d I by dt, this will give me a delta function here. And because of that, there is this j r t, which is equal to 0 for t less than equal to 0, and it is I naught delta x delta y in the z direction for t greater than 0. And the derivative of j gives you that delta function, and once we put all that in, this is the expression that we get. Because of the symmetry of the problem, the E field depends only on S, no phi dependence. I put it next to the wire, but let me rewrite it so that you do not miss it. Electric field E depends only on S and time, no phi dependence. Because of the symmetry. So, now we have got our expression. Let us evaluate this. So, I have E S t equals minus mu naught I naught over 4 pi in the z direction, and then I have this integral d z prime delta of t minus square root of s square plus z square over c divided by square root of s square plus z prime square. And this is for t greater than square root of s square plus z prime square over c, and this is 0 for t less than that. What this means is, if I were to look at this condition here, this means is that c square t square is greater than s square plus z prime square. C square t square minus s square is greater than z prime square, and therefore, this integral will be non-zero only for mod z prime less than square root of c square t square minus s square. What does it mean physically? Physically, what it means is that here is this wire on which we suddenly turned on current at t equals 0, and the signal moves from everywhere to this point at a distance s. Since the speed of light is c, then c t equals s square plus z prime square. This is the maximum from where the signal can come. So, let us write this. This is the only length from where signal about current reaches. point shown. And we are calculating the field corresponding to that. So, now everything else is very easy, and therefore, E S t is equal to minus mu naught I naught over 4 pi in the z direction. And now, the integral I know is going to be from minus square root of c square t square minus s square to plus square root of c square t square minus s square. That makes perfect sense. What that means is signals from here, this region, only are reaching the point where I am interested in the field. And inside I have the delta function, delta t minus square root of s square plus z prime square over c divided by square root of s square plus z prime square dz prime. This is what I ought to calculate. To calculate this, what I am going to do is write my delta function, which now is a function of z prime as far as the integration is concerned, s square plus z prime square over c is equal to summation 1 over modulus partial f over partial z prime at z prime equals z 0 I, z prime equals z 0 I, meaning where the argument is equal, delta z prime minus z 0 I. This is what I am going to substitute for the delta function, and then I am going to integrate. So, when you do that, you get E S t equals minus mu naught I naught over 4 pi is in the z direction, summation I 1 over partial f partial z prime at z prime equals z naught I 1 over square root of s square plus z 0 I square. That is going to be your answer. Now, my function f is t minus square root of s square plus z prime square over c, and I know that z naught 1 is square root of c square t square minus s square, and z naught 2 is equal to minus square root of c square t square minus s square. So, I have these two roots where the delta function gives you that contribution, and you substitute this in, calculate d of dz prime square, do the integration which I am leaving for you, and you get E S t to be equal to minus mu naught I naught c over 2 pi square root of c square t square minus s square in the z direction. So, rest of the filling in you have to do. So, this is my electric field from direct calculation from the formula for it. How about calculation of B? For calculation of B, we have this formula B R T equals mu 0 over 4 pi integral grad prime cross j r prime t prime, where t prime is evaluated at t prime is t retarded, divided by r minus r prime d v prime. Now, you see, when we wrote j for time t greater than 0 is I naught delta x prime delta y prime z, and you can see if I take the curl will involve derivatives of delta functions. So, this calculation tends to become a little cumbersome. This is what I had remarked, that calculating the fields directly sometimes can be problematic. For example, in the calculation of E, if I had a delta function charge, I would run into a problem, because we take the gradient of the charge density. So, that is why one goes to the potential formulation. So, here I am not going to do that calculation. Instead, what I am going to do is use Faraday's law, which says that curl of E should be equal to minus dB dt. I have already calculated E, so calculating curl is very easy, and then integrate with respect to time, and you get the answer for B. So, let me quickly outline this. We have already calculated E as t is in the z direction, and it comes out to be minus mu naught I naught over 2 pi square root of c square t square minus s square, and on top is c in the z direction. This is only z component. So, curl of E is going to be equal to minus d E d s in the phi direction. You work it out, and curl of E then comes out to be mu naught I naught c over 2 pi s over c square t square minus s square raised to 3 by 2 pi, and this is equal to minus dB dt. So, one thing is clear, B is in phi direction, and you can also do the integral very easily with respect to time. You do that by substitution, and you are going to get B S t equals mu naught I naught over 2 pi s c t over square root of c square t square minus s square phi. When you do this, you are going to get a constant when you do the time integration, and that constant should be fixed in such a manner that as t goes to infinity, you recover your steady state B results. Or if you get integrate from 0 to time t equals 0 to infinity, then you will get an infinity. Oh, sorry, if you integrate from 0 to time t, you will get in the constant infinity, which you can ignore and write your answer like this. I will let you work this out yourself. So, I am leaving this for you. Fix the integration limits slash integration constant appropriately. That is one thing. The other thing I am leaving for you is compare the answers with those given in Griffiths. So, this problem is done. Next, we extend this problem. Again, I am taking from Griffiths, who has extended this problem, and solve that. Problem 2, this is again from Griffiths. This is chapter on retarded potentials and I think this is chapter 10 in 4th edition. In the newer edition, the chapter number has changed. I think the problem number is 10.10, 4th edition. It says an infinite wire carries the current I t equals 0 for t less than equal to 0 and k t for t greater than 0. Find the electric and magnetic fields from direct formulas. This part I am making up. I want you to calculate this from direct formulas, number 1, and number 2, check the answers by calculating potentials. So, this problem is also very similar to the problem we just solved, except that the nature of current has changed. The way current is going is 0 up to t equals 0 and then it increases linearly. So, let us first plot the current. The way current is going is 0 and then increases linearly. Again, you will see how we use retarded time when performing these calculations. Now, let me quickly write that J R t is equal to 0 for t less than equal to 0 and it is equal to k t delta x delta y in the z direction for t greater than 0 and rho r t is 0 again. So, there has been no contribution from the charge density, the only contribution comes from the current density. So, let us again first calculate electric field for this problem. The electric field E again is going to be bisymmetric, dependent only on S, is going to be cylindrically symmetric. So, all that we are assuming, and I will let you think about it, and S t therefore, is going to be equal to minus mu naught over 4 pi integration d by dt prime j r prime t prime. This is being calculated at t retarded divided by r minus r prime d v prime. The second term is 0 due to rho, because there is no rho. The time derivative is k t. So, this I can write as equal to minus mu 0 over 4 pi integration k, and but this is going to be at retarded time over r minus r prime d z prime. That is my answer. What does this k retarded time mean? This means, you see this current I is being calculated at t prime is going to be equal to 0 for t prime less than equal to 0 and is going to be equal to k t prime for t prime greater than 0. What is t prime? T prime is equal to t minus r prime over c. And again, because of that spherical, because of the cylindrical symmetry, and again because of the cylindrical symmetry and all that we are doing in the previous problem, this is going to be equal to t minus square root of s square plus z prime square over c. Let me just remind you what we are doing. Here is the wire on which the current is going. S is the perpendicular distance from it, and we may as well calculate this whole thing at z equals 0, because there is no dependence on z, and this direction is z. Therefore, this k retarded time means k retarded time means this is equal to 0 for t prime less than equal to 0. So, t less than equal to mod or under root s square plus z prime square over c, and this is equal to k for t greater than square root of s square plus z prime square over c. Again, all causality. So, this fixes everything. Like the previous problem, this fixes the z prime integral is going to be from minus square root of c square t square minus s square to plus that. So, what I am going to have then is E s t equals minus mu naught k over 4 pi as in the z direction integral dz prime over square root of s square plus z prime square from minus square root of c square t square minus s square to plus c square t square minus s square. That will be my answer. Now, I can do the integration very easily. What is important in this is how we arrived up to this expression. You see, we used retarded time, and we have to understand what retarded time means. Wherever the time thing was coming, I am replacing it by retarded time. So, although when I looked at k retarded time, it looked like a constant, but I have to be very careful. So, let me just spend some time on that before I do the integral. So, what we were calculating is this E s t, which is minus mu naught over 4 pi z integral k retarded over r minus r prime d v prime. This I replaced by d z prime, because I took care of delta x prime delta y prime through that. Now, what this means is this k retarded, it is representing the derivative of j with respect to time at t retarded. And we have been given that j is not equal to 0 only for t greater than 0. But if I calculate this for retarded time, this means j calculated at retarded time is not equal to 0 only if t retarded is greater than 0. What that means is that after I turn the current on, it takes some time before it reaches a certain point. So, now we can do the integral very easily. My electric field E s t is equal to minus mu 0 k over 4 pi in the z direction integral minus square root of c square t square minus s square to plus c square t square minus s square dz prime over square root of s square plus z prime square. You can substitute z prime equals s tangent theta and do the integral, and the answer you finally get is minus mu 0 k over 2 pi log of C t plus square root of c square t square minus s square over s in the z direction. Put this like this. That is the answer for E. If I were to calculate the magnetic field now, B, this will again involve the curl of J at r prime t prime over r minus r prime d v prime. And again, since J has this delta function and everything, it is a difficult calculation to do. So, again we will use curl of E equals minus d b by d t and get our answer. The answer comes out to be B S t equals mu 0 k over 2 pi S c log of C t plus square root of c square t square minus s square over s in the phi direction. That is the answer. Next, what I want to do is check the answers obtained by calculating the potentials, which, as I said, is going to be an easier calculation. So, for the same problem, I have I t equals 0 for t less than equal to 0 and k t for t greater than 0, and we have worked out J and everything. The vector potential A r t is given as mu naught over 4 pi integration. Now, there are no derivatives involved, d v prime j r prime t prime, where t prime is t retarded, divided by r minus r prime. Again, j r t is k t delta x delta y in the z direction for t greater than 0. And everything is, again, it is a long wire, so things depend only on S. So, all that symmetry arguments does not depend on phi, all that we do, and we get A S t equals mu 0 over 4 pi in the z direction integral of k t retarded divided by square root of s square plus z prime square. Delta function integrals have already been done. So, this is going to be d z prime. T retarded means t minus square root of s square plus z square over c, and this is true only for this greater than 0, and otherwise is 0 for t minus square root of s square plus z prime square over c less than equal to 0. This is z prime square. Since I want t retarded to be greater than 0, this again means t minus square root of s square plus z prime square over c greater than 0, and this implies that c square t square minus s square square root is greater than mod of z prime. So, again as we discussed earlier, if I want to calculate, I am going to the wire now, the A potential at this cross point, the only contribution comes from this distance between minus c square t square minus s square to plus square root of c square t square minus s square, because only from this part of the wire can the signal reach S. Beyond that, the time is too short to reach this point. So, the integration is going to be between these limits, and therefore, the vector potential A S t is going to be equal to mu naught k comes out over 4 pi, it is in the z direction. Integral is going to be from minus square root of c square t square minus s square to plus c square t square minus s square. Inside I have t retarded, which is t minus square root of s square plus z prime square over c divided by square root of s square plus z prime square times dz prime. Delta x prime, delta y prime, dx prime, dy prime integrals give me 1. So, that part is gone, and whatever is left is basically what we had was A S t equals mu naught over 4 pi z integral j r prime t prime equals t retarded divided by r minus r prime dv prime, and that goes over to this. Now, this is an easy integral to perform. So, I get A S t equals mu naught k over 4 pi z. I can multiply by 2 and do the integral from 0 to square root of c square t square minus s square t minus 1 over c square root of s square plus z prime square divided by square root of s square plus z prime square dz prime. The integral dz prime over s square plus z prime square square root integral we have already done. The second one is also very easy to do. It will just be z prime between those two limits. You perform the integral and you get A S t equals mu naught k over 2 pi in the z direction times t log of square root of c square t square minus s square plus c t divided by s minus 1 over c square root of c square t square minus s square. That is the answer. For the vector potential. Once I have obtained the vector potential, it is very easy to get the fields. The electric field E S t is going to be minus d A d t, since phi is 0. And that you can do very easily, and you get the answer to be minus mu naught k over 2 pi in the z direction log of square root of c square t square minus s square plus c t over s, which is the same answer as earlier. And you can also calculate B very easily. B is going to be curl of A, and that part I am leaving for you to do. Calculate B equals curl of A from A obtained, and check that it satisfies curl of E equals minus dB dt. So, you compare the calculation that we did for E and B from direct formula, B we did not do, but calculation for E that we did from direct formula, and compare that with the calculation route through the potential, and you find that potential route is easier. So, these problems show that finding the fields through potentials is easier than applying direct formula. Why? Because the formula for fields directly involves derivatives of the current density and charge density. This can be done, but it is a little more difficult. So, let me conclude this lecture. We have solved a couple of problems involving time dependent current density. We learned how to handle retarded time, and also learned that calculation is easier when fields are calculated by obtaining potentials first. Thank you.